Welcome back to BAS 120. This is part 2 of chapter 5. So we walked through in part 1 some of the basic concepts of probability. Now we're going to talk about a probability distribution, how we're going to actually be able to use probability to take our random variables and our distributions to actually use it to predict outcomes. So this is where probability becomes very powerful to us. So a couple terms again. A random variable is just a variable typically represented by an x that is a single numerical value that is determined by chance. And we can have discrete random variables, which are random variables where the outcomes can be counted, like a dice roll or a flip of the coin, or they can be continuous, like time or a rate of return. We're all real numbers, so continuous is like we're all real numbers between 0 and 1. Discrete would be integers from 1 to 10, rolling of a dice, etc. And the reason this is important is these will be handled a little bit differently. So let's talk about the difference between data versus a variable, because sometimes this might come in handy. So data might be, let's think of an example where an experiment where we flip a coin 2 times. So if you think about flipping a coin 2 times, we've got 4 possible outcomes. We could get 2 heads, probability that's 1/4. We could get 2 tails, probability that's 1/4. We could get a heads on the first one, a tails on the second, and a tails on the first, and a heads on the second. So the probability of getting 1 head is 50%, because there's 2 ways we can do it. So the probability intuitively of getting 0 heads, i.e. 2 tails, is 0, is 25%, 1/4. Probability of getting 0 heads. Probability of getting 1 head would be 50%, and the probability of getting 2 heads would be 25%. Now, data, we might go out and we might flip the coin 100 times. Now, most likely in our data, we're not going to get exactly 25%, 50%, and 25%. So in this, and I went to a random numbers generator, and we randomly, 21% of the time we got 0 heads, 49% of the time we got 1 heads, and 30% of the time we got 2 heads. That's our data. Now, if we talked about the underlying variable and what is the probability of that variable, that's when we would talk about 25%, 50%, and 25% based on the probability of that variable happening. Notice that the data and the variable probabilities, particularly as I do more and more samples, are going to align very, very closely. They're never going to be exact, but they're going to align very closely. So that's kind of the difference between data and a random variable. We use a random variable to predict the probabilities. So let's talk about, we've talked about random variables, whether they're discrete or continuous. Let's talk about a probability distribution. So a probability distribution is a graph or a table that gives us a probability for each value of the random variable. So this is a normal shaped curve, and here is all our random variables down here, expressed as a standardized score, which we'll get into later, but expressed as a certain score. And you can go along here and you can say the probability of this is this probability. This is a different probability. And you've got several different kinds of probabilities. There's a binomial distribution, a Poisson, a normal, an exponential, and that's, you could go on and on and on and on with different kinds of probability distributions. And in the example videos, we go through about 5 or 6 of the different distributions and show you exactly how to calculate them using statistical Excel software and how you go about that. But the probability distribution is simply this distribution in a graph or a table, which shows the probability for each value of the random variable. Now, sometimes we need to know to get there. So how do we get to that probability distribution? Well, first we have to know the mean, the average. We need to know what the center is. Now, oftentimes that's used by calculating what we call our expected value. Okay? So if we went golfing and I said, what do you expect to score today? What's your expected score on the golf? Well, intuitively, you would say, well, normally I shoot 90. And last week I shot a 95, a 90, and an 85, and I add those all up, and I might take an average of all my golf scores, and I might say, see how I did to get an expected value. That's exactly what you do. You take, and here's the formula, the expected value is where I sum up all my outcomes, X, basically in this case is my score, times the probability of getting that score. And the way I get to the probability of getting it, so, if on day one I shot a 95, there's a 10% chance I'll shoot a 95, there's a 60%. I'm basically, by multiplying by this probability, I'm taking a weighted average of all my outcomes. Another way you could do this formula is you could say my outcomes divided by the n, divided by the number that I've done. So what is my average? By multiplying by the probability, I'm basically taking a weighted average of all my previous golf scores. That's all it is. This sounds like a very, very complicated formula, but if you think of it, all we're doing is we're saying, hey, just sum up all your outcomes times the probability of that outcome. How did I get to the probability of that outcome? I took an average. Now, the expected value is oftentimes what we use for the mean. So it's, how do you use it in business? Well, it's used often, right? For hotels, airlines, reservations. How many cancellations can I expect? What's the expected value of the cancellations? Most hotels, airlines, and their reservations do what's called overbooking. Well, in business, it's pretty important to have a pretty good handle on to what extent that overbooking I should do. If I do too much overbooking, I have a problem of people shows up at my hotel and I have to tell them I don't have a room. That obviously is not good for my customer satisfaction. I obviously have to refund their money and normally give them some sort of additional compensation. So you don't want that to happen, but you don't want to, if 50%, if your data tells you 50% of your reservations get canceled, you certainly don't want to stop making reservations. You want to do some degree of overbooking. So a lot of science goes into that with what level of expected value can I expect in terms of cancellations. And it gets very sophisticated, right? It might change. It might go up in the summertime. Also used for raffles or lotteries, right? What should the prize be? Can I afford to give away a car? Well, what is my expected value over this? Now, once I know the probability distribution, so I can figure out the mean or I can calculate the mean with the expected value. Once I have the mean, now I need to know how much variation there is. Well, if we know the mean, the variation, which we'll show you the equation in a minute, is just a measure of how far each one of our outcomes is from the mean. If every outcome is exactly the mean, exactly the average, then I have no variation in my data. If the test scores were all an 80, 10 test scores, they all scored 80, then the mean is 80 and I have no variation because there's no difference. No score varies from the mean. They're all the same score. Most of the time we have some outcomes that vary from the mean. So how do we calculate it? Now here I put the formula that's normally most people utilize, but I've also told you some things that you could substitute in here, which the book substitutes a couple of days. So let's talk about the variance. The symbol for the variance and the standard deviation is just the square root of the variance. So I add up all my scores, all my outcomes, and I compare them to the mean. Now, I could substitute for the mean expected value, right? So sometimes they would say each test score compared to the expected value or compared to the mean. Now, I square them, and in the example I go through why you square them, But a quick one here is, if I don't square these numbers, then my deviation from the mean, when I add them all up, I'm going to get 0 because the negatives and the positives are going to offset each other. So to make them all positive numbers, we're going to square them, square each one of these. Then we divide by n to get the average. Now, another way we could do it, just like we could multiply by the probability of the event. That's just another way of taking a weighted average. So we could, in this equation, if we wanted to, substitute expected value for mu, and rather than dividing by n, we could multiply by the probability of each individual event. So that's how we calculate the variance, and there's an example that goes through in Excel, blow by blow, how to do it. But I wanted to walk through a little bit of this equation, and then the standard deviation just takes the square root of the variance. Now, once we have our mean and our variance and our standard deviation, normally we're going to normalize this score. So we can say, well, how many standard deviations away from the mean are we? And a standardized score puts it folks, large numbers and small numbers basically on the same playing field, so that we can then go to statistical software, or we can then go to probability table and find out the probability. So for a normal curve, and there's all sorts of standardized scores, but a Z-score is a common one for the normal curve. It's our x value compared to the mean, whatever our value is. So if I got a 70 on a test score, how far away from the mean is that? If the mean is 80, I'm negative 10 away. And I divide by the standard deviation, which standardized my score. Basically tells me how many standard deviations to the left or the right is my score. So if I got a 70 on the test, and the average was 80, and the standard deviation was 10, I would have 70 minus 80, which would be a negative 10, divided by 10, which would give me a Z-score of negative 1, which tells me I'm negative 1 standard deviation away from the mean. And again, I go through a ton of examples in Excel. Numerous probability distributions, and again, there's an example of every one of them. A binomial is a discrete distribution. We go through what a binomial is, basically where you have a yes-no experiment. In Excel, there's a tool called BIMONDISC. Poisson distribution is another one. Is a series of independent yes-nos. There's a normal distribution. And along with these discs, there's a thing called, so a disc is where you know an outcome, but you wish to know the probability. There's also within Excel an INV, where you know the probability which you wish to know the outcome. All of this will be much clearer as you go through the videos that go through every single example of all of these, but this summarizes it for you. Let's talk about random sampling quickly. So now, once we have a probability distribution, now we can go into Excel, and it provides a randomized function which generates a random number between 0 and 1. So once we have the random number, now we can generate multiple scenarios or simulations. And if we add in the analytic solver, we can do sensitivities. We can instantaneously run 1,000 simulations, which is an example we go through. And it gives us the power to take probability, put it into a distribution, and then once we have that distribution, we can now run multiple simulations so that we can say, so for uncertainty, we can explain the uncertainty of lots of business events or outcomes. So the applications are just all over the place. It can be in service levels, budgets and forecasts, customer demands. And again, we go through a half dozen examples. We also have a tool that tells us, well, which probability distribution does our data fit? Because there's tons of probability distributions. And part of the challenge is to say, well, which distribution fits our data the best. And within Analytics Solver, there's a tool, which again we show you in the examples that walk you through all how to do that. So that's Chapter 5. Just in summary, we talked about some of the probabilities and roles. We talked about conditional, independent events, multiplication law, difference between discrete and continuous, probability distribution. We talked about normal distribution. We talked about the Z-score, randomizing, random number generator in Excel, and how to fit distributions using Risk Solver. Now, go through all the examples that we have for you, and as you go through each Excel example, this overview should become very clear with the examples. Thanks.